Hello everyone, I'm Pen-Sheng, coming from National Tsinghua University, Taiwan. I'm so happy being here to introduce my research, hybrid silicon etching for performance enhancement of the atmospheric CMOS-MEMS infrared sensor. This is my outline. First, I will make an introduction of MEMS IR sensor and the existing silicon etching process. In the motivation and design concept part, I will show you what's the benefits of the hybrid silicon etching process. Next, I would like to show the fabrication and measurement results. Finally, I will conclude today's speech. MEMS IR sensors have many applications, including motion detection, gas sensing, thermometer, and night vision. However, for certain applications, such as gas sensing, MEMS IR sensors should be operated in the atmosphere. So we need to discuss the design factors of the atmospheric MEMS IR sensors. This page shows the heat transferring mechanism of MEMS IR sensor in the atmosphere. As you can see, the responsivity is proportional to the total thermal resistance, RTH. And the total thermal resistance consists of two items. One is the thermal resistance of isolated thin film, and the other is thermal resistance of air conduction to a substrate. In the atmosphere, the thermal resistance of the thin film is much larger than the one from air conduction. So we can learn that in the atmosphere, the heat transfer of MEMS IR sensor is dominated by air conduction. Furthermore, the thermal resistance of the air conduction is proportional to the etching depth. So we can enhance the atmospheric responsivity through increasing the etching depth. Practically, the etching depth of MEMS IR sensor is dominated by substrate etching process. Moreover, we are usually looking for the CMOS-compatible process because they are better for building SoC MEMS IR sensors. There are three typical CMOS-compatible silicon etching process. The first one is anisotropic wet etching, like TIMA and EDP. For this kind of process, the 111 facet of silicon crystal can serve as the etching stops, so the precise etching time control is not needed. However, because of the specific interfacial angle in the silicon crystal, the etching depth is limited by sensor's footprint. And the second one is xenon difluoride, a kind of gas-phase silicon etching process. It's a pure chemical reaction process. So it's fast, it's no stick issue, and also no plasma damage issue. But it's an isotropic process, so the etching boundary should be carefully monitored. The last one is deep ion reaction process. It can achieve high aspect ratio structures, but it needs ultra backside process, which needs more cost and may produce alignment issue. In the next part, I will present the motivation and design concept of this work. Based on the previous review on the topic of etching process, all of them have their own advantage and limitations. In this research, we propose a novel etching process which combine to establish a silicon etching process. They are DRIE and xenon difluoride respectively, and I will tell its benefits. First, the hybrid process is CMOS compatible because they make the process more easily implemented on standard platform and applied in SoC MEMS IR sensor. The second benefit is that the process can deepen the etching depth without any limitation from sensor's footprint, then enhancing the sensor's responsivity. Lastly, this is an front-side etching process, and the sensor structure can serve as a hard mask, so there's no need for additional masks and no alignment issue. This hybrid process consists two etching steps. The first step is using DRIE to etch the silicon substrate to our target etching depth. In this step, the sensor structure serves as a hard mask. The second step is using xenon difluoride to release the sensors by removing the rest part of silicon substrate underneath the structure. To prove the effect of this novel process, we have three proposed design and one reference design. These sensors are all thermoelectric CMOS-MEMS IR sensors, which use the doped polysilicon layer in the TSMC standard platform to construct the thermocouples. The plane geometry of proposed and reference design are the same. but the proposed design was fabricated with the hybrid process, and the etching depths are designed as 50 micrometers, 100 micrometers, and 200 micrometers, respectively. On the other hand, the reference design was fabricated with Xeon difluoride process, and the etching depth is only 10 micrometers. Moreover, we also designed 3 kinds of film thickness of MEMS IR sensors to verify whether increasing etching depth has more significant effect when the thermal resistance of the thin film is larger. To evaluate the performance, we simulate the total thermal resistance of the design sensors. The result shows that in the atmosphere, the responsivity was enhanced along the increasing etching depth. The improvement is more significant, especially for the thinner structures, which means higher thermal resistance of thin film. That's due to the total thermal resistance is more likely to be dominated by gas conduction when there is large difference of thermal resistance between thin film and air conduction. Next, I will show you the fabrication and measurement results. This page shows the implicit fabrication process flow. First, I got a well-stacked CMOS chip from TSMC. Second, the metal superficial layer on the chip was etched by the metal wet etching process, and then the second etching window was defined. Thirdly, we used DRIE process to deepen the etching depth to the target value. Fourthly, the Xeon difluoride process was conducted to release the sensor structures, and then the thermal isolation was completed. Finally, we used the laser drilling to open the pad and fulfill the electrical connection. The result of fabricated device are shown here. The plane geometry of the demonstrative sensor has been well defined, and from the zoom-in OM graph, we can see the polysilicon thermocouples has also been well defined. And through the cross-section view of SEM graphs, we can measure the etching depth. The depth of the proposed design are 17493 and 204 micrometers respectively, and the depth of the reference design is 15 micrometers. These etching depths are quite different from our design parameters. However, each etching depth have considerably distinct value, so we still can do the comparison of their performance. The measurement result of the sensor's responsivity are present here. We can see that for the sensors with the same film thickness, the responsivity has been significantly improved. The etching depths have increased from 15 micrometers to 17 micrometers. However, when the etching depths are further increased, the responsivity enhancement cannot be well discerned. So we use the simulation of total thermal resistance to express the phenomenon. As you can see, the etching depth was increased when the etching depth was increased from 15 micrometers to 74 micrometers. The total thermal resistance largely increased. That caused the significant increase of the responsivity. In contrast, when the etching depth was increased from 74 micrometers to 204 micrometers, we only got smaller increase of total thermal resistance. And if the resolution of the measurement setup is not good enough, this increase cannot be verified through the responsivity. Moreover, through the measurement results, we also compared whether the increase of etching depth has more outstanding effect on sensors with thicker film or thinner film. In the previous simulation, the result predicted that the sensor with thinner film has more obvious enhancement. However, in the measurement, the result has complete opposite. We estimate that this phenomenon is due to all the film thickness are smaller than the penetration depth in infrared range. Namely, the incident radiation do not be totally absorbed by the sensors. And the sensors with thinner film would absorb less amount of radiation that is responsible for the lower responsivity. To deal with this kind of problem, we can deposit material with high absorptivity on the sensors, for example, metal black paint or some porous material. Or we can design some optical absorber like Magta material absorber, which has high absorptivity but thin thickness. Finally, I'm going to conclude this presentation. In this study, we demonstrate the feasibility of a CMOS-compatible hybrid silicon etching process, and this process can increase the etching depth without any constriction of sensor's footprint. Finally, the increase of etching depth through our proposed process to improve the sensor's responsivity in the atmosphere. Lastly, I would like to thank MOS, CMM, and TSRI in providing the fabrication platform, facilities, and research funding. Thank you for your attention. If you have any questions, please feel free to email me.